Is your Python code a tortoise when you need a hare? What if I told you that you could supercharge it with the power of not one, not two, 5 different languages? In the next few minutes, we're not just coding. We're giving Python a phenomenal speed boost in less time than it takes to make a cup of coffee. Let's look at the top 5 languages for taking your Python code from sluggish to supersonic. Choosing Python for a project often comes with the acknowledgement of its not-so-secret flaw: execution speed. But should this lead to a complete rewrite, shifting to an entirely different programming language? Not necessarily. The key lies in optimization, not overhaul. By honing in on the hot paths, the most performance-sensitive parts of your code, you can significantly boost efficiency where it matters most, allowing Python to continue shining in areas where it excels: readability, simplicity, and a rich set of libraries. The first language is technically two: C and C++. These are the classic languages for extending Python, and many popular libraries are written in C or C++. As highly performant, low-level languages, their speed is typically used as the baseline when comparing programming language performance. While commonly used in system-level programming, C and C++ have wide-ranging uses. Python itself is written in C. As a result, C and C++ are really well supported for writing Python extensions. Python ships with a C API that you can interface with. Here's a snippet of a Python module written in C. It takes a list of tuples of integers that represent coordinates on a two-dimensional plane and calculates the distance you'd walk if you were to traverse them in order. The full code is on GitHub, link in the description. This can then be compiled using the built-in setup tools module and imported into your Python code. Lots of really popular libraries use C and C++ to provide massive speed boosts. The most well-known examples are number crunching libraries like NumPy, SciPy, and Pandas, but other examples include graphics libraries like Pygame or Kivy, or parsers like LXML. However, one of the problems with writing C and C++ code is memory safety. It's hard to write code in C or C++ that doesn't experience memory leaks, and seg faults are aplenty. It can also be difficult to write performant code if you don't really know what you're doing. If that doesn't sound like fun to you, you might prefer the second language on the list, and that is, of course, Rust. Rust has gained a lot of traction in recent years for its impressive speed, intense focus on memory safety, and generally excellent developer experience. Rust is becoming particularly popular in the Python ecosystem, with popular libraries like Pydantic adopting Rust to boost performance. There's also a rise in Rust-first libraries and tools, like Ruck, the ultra-fast Python linter, or Robin, the Python web server framework built almost entirely in Rust. Python's extensive ecosystem provides a few options for writing Python extensions. The most commonly used is PyO3. It provides memory and type safety out of the box, so the code is generally much terser and easier to read. Here's the Rust equivalent of the C extension we wrote earlier, using the PyO3 bindings. As you can see, it's reasonably short by comparison, and Rust is pretty easy to follow. Compilation can be done using a tool like Maturin. If you're interested, check out this video for how to get started with writing Rust extensions for Python. But what if you don't want to learn Rust? The learning curve is quite steep, and it gets very difficult if you want to start making better use of your CPU cores with concurrent programming. This is where the next language excels. Naturally, I'm talking about Go. Go is known for its super simple language design, high performance, and excellent concurrency primitives. Go isn't commonly thought of as a Python extension language. However, it's unbelievably easy to learn and really shines in high throughput concurrent programming. So I wanted to include it here. As an additional benefit, Go is garbage collected, so you don't need to worry about memory management. The most popular way of extending Python with Go is using the GoPy library. Setup requires installing a couple of Go CLI tools, GoPy and Go imports. Go is naturally a little more verbose than Rust, especially when it comes to error handling. However, GoPy makes things really easy, and creating the module is as simple as creating a standard Go module with an exported function, like this. You'll notice this code uses a struct rather than a tuple, as they are yet to be supported by GoPy. Lists are also unsupported by default, so I had to create the coord list type to force GoPy to create a wrapper. The calling Python code, however, is still very simple and easy to understand. I'm a big Go lover, so I'd love to do a deeper dive into extending Python with Go. Let me know in the comments if that's something you'd like to see. Okay, you don't want to look at code with all those ugly curly braces and static types. I get it. So let's look at something a little more Pythonic. Our next contender is a high-performance, just-in-time compiled language designed specifically for scientific computing and has a Python-like syntax. Julia is a dynamically typed language designed for parallel number crunching. It uses a concept called dynamic dispatch to allow writing composable, easy-to-understand code. Julia takes a lot of inspiration from Python, which you can see in some of its syntax. You can create a Python extension using a couple of libraries, PyJulia for Python and PyCall for Julia. Install PyJulia with pip install Julia. PyCall will be installed automatically later. Here's the Julia code for the distance function we've been using as our example so far. As you can see, it almost looks like Python code with fewer colons. On the Python side, you just have to first set up the Julia Python bridge using julia.install. This will install PyCall and set up other requirements. I recommend having this code in a setup script. It only needs to be done once, but can take some time. This is because Julia is just in time compiled, so you have to ship the Julia code along with your Python library. Once you've done this, load your Julia file and call the functions you need. Setting up the bridge can take a while though. It also requires the end user to have Julia installed. Thankfully, there's a compiled language that looks and operates a lot like Python that you can use for speeding up your code. And that language is Nim. Nim is a statically typed, compiled systems programming language that takes a lot of inspiration from Python, Ada, and Modular. It has a C++ and Rust-inspired memory model and some really useful compile time features, and it looks a lot like Python. Nim was designed to compile to C, C++, and JavaScript, which makes it super flexible. It's also ideal for writing Python modules. Get started by installing NumPy, the Python bindings for Nim, using Nimble, Nim's package manager. The Nim code looks very Python-esque with its significant whitespace and mostly familiar syntax. The Python export is marked using the export py directive in the function declaration. Then, you can simply compile it to a binary using the following. Running it from Python is as simple as other compiled languages. Just call it and execute the function. If you're curious about which is faster, take a look at this graph. I was unable to get Julia to run, unfortunately, as PyJulia does not allow statically linked Python binaries like those installed using Linux package managers. However, the rest of the results are really interesting. C actually comes out slowest, though that's probably my implementation. All the other languages mentioned are at least twice as fast as the Python implementation. Nim and Julia look a lot like Python, and that's great. But what if you don't want to learn a new language at all? Then you have a couple of bonus options. Cython is a static compiler for Python and the extended Cython language. It allows you to compile Python code to a binary and run it directly. The other alternative is Mojo, a language designed as a superset of Python and aimed at data science applications. It also allows you to compile Python code, and you can optimize further just by adding a few Mojo type hints. If you want to learn more about Mojo, you can watch the video I have on it here.